All right, let's jump right into this explainer. We're going to trace the incredible evolution of AI, going all the way from rigid hand-coded rules to the models we have today generating human-like text. Let me ask you a question right up front. When you write a simple if-else condition in a piece of code, are you technically building artificial intelligence? Well, historically, sometimes the answer is actually yes. But honestly, that's just the very beginning of the story. Today, we're going way beyond the surface-level buzzwords to look right under the hood and see exactly how these systems solve problems. We're exploring the evolving mathematics of problem solving.
Here's our roadmap for today's chronological journey to demystify how these systems actually work using a true engineering mindset. We'll cover 1. The AI umbrella. 2. Era of strict rules. 3. Machine learning, learning from data. 4. Deep learning and AlexNet. 5. Transformers and attention. And finally, 6. Choosing the right tool.
Section 1. The AI umbrella. Scope of AI. We're kicking things off by completely busting the myth that AI is just one giant monolithic technology.
So, the absolutely crucial point here is that artificial intelligence is literally a broad canopy. It covers entirely different mathematical approaches to problem solving. It's an umbrella term for a whole field of systems designed to do things we normally associate with human intelligence. Underneath this umbrella, you've got distinct subfields built for completely different kinds of problems. Because of this, it's totally vital to recognize that while chat interfaces get all the hype right now, ChatGPT is just one specific slice sitting right at the very edge of that much larger AI umbrella. When people talk about tools like ChatGPT, you have to remember it's not the definition of AI itself, but merely one approach among many. When you map it out from the 1950s to today, you can really see how we moved from rules and symbolic AI, where humans literally encoded knowledge as logic, through machine learning and deep learning, all the way up to the transformer architectures powering today's generative AI. Section 2, era of strict rules, hard-coded logic. Let's travel back to the early days, where we tried to create intelligence by hard-coding pure, strict logic directly into computers. Think about a classic payroll system. The logic here is highly deterministic. Step 1, if the salary is negative, flag the record. Simple, right? Step 2, if the employee ID is duplicated, flag it. Step 3, unapproved bank account, stop the payment. When your environment is perfectly stable, this step-by-step deterministic logic is absolutely bulletproof. So take a second to think about this. What's actually safer for preventing a negative salary? A simple deterministic rule or a massive large language model? If you guessed a deterministic rule is safer here, you hit the nail right on the head. You do not need a massive neural network to check a basic math error. You just need a hard-coded condition. But here's the catch. This strict approach hit a massive brick wall. Why? Because human experts use highly complex pattern recognition that simply cannot be written out as microscopic rules. Real life is incredibly messy. There's just no way an experienced doctor reading an X-ray could mathematically write down every tiny rule their brain just intuitively used to spot an anomaly. There are simply way too many edge cases. Which brings us to Section 3, machine learning, learning from data. That massive frustration with manual rules sparked a total paradigm shift, leading us perfectly into our next era. It completely flipped our approach to problem solving upside down. Think about spam emails. Instead of hand-holding algorithms to spot a spam email by trying to manually write a rule for every possible spam keyword, which honestly fails miserably, we just fed them data. We provided thousands of examples of spam alongside legitimate emails, allowing the system to tweak its own internal math and find hidden statistical correlations. This shift was revolutionary because for the first time, machines were discovering correlations entirely on their own. The system literally finds the hidden patterns straight from the data itself, giving us some serious predictive power. However, engineers pretty quickly hit another wall. Traditional ML couldn't automatically process the complex visual features of unstructured data, like images or audio. A human still had to manually tell the algorithm what specific edges or colors to look for. That was totally fine for structured business data, but way too difficult for raw visual or audio information. Section 4, Deep Learning and AlexNet, Hierarchical Patterns. To conquer that complex visual data, we needed multi-layer neural networks, which brought us to the breakthrough of deep learning.
These multi-layer neural networks acted kind of like a giant puzzle, progressively building hierarchical understanding from raw pixels all the way up to highly complex concepts. The network discovers visual patterns entirely on its own by adjusting millions of internal numbers across these interconnected layers.
1.3 million. That massive number represents the exact amount of images a specific 2012 model was trained on just to master pattern recognition.
That model was AlexNet. It's a landmark pioneering deep convolutional neural network, or CNN, that absolutely revolutionized computer vision. Developed by Alex Krzyzewski, Ilya Sutskever, and Jeffrey Hinton, it proved that deep learning models could drastically outperform traditional machine learning techniques in image classification. By combining massive datasets, optimized neural networks, and raw GPU number-crunching horsepower, AlexNet won the 2012 ImageNet Challenge by a massive margin. It was a true watershed moment. So, we had conquered images, but AI hit yet another wall, this time with broad language. Early deep learning processed text linearly, just word by word, making the models notoriously bad at remembering context if words were too far apart in a paragraph. Section 5. Transformers and Attention, Mastering Context. To fix this linear bottleneck, researchers in 2017 introduced a revolutionary mathematical concept. To really grasp this, look at this sentence. As humans, we just instinctively know it refers to the service. But historically, mapping that relationship was an absolute nightmare for a computer. The attention mechanism solves this exact mapping nightmare by assigning mathematical weights to every word's relationship with every other word. So the crucial point is that this allows the model to instantly map it back to service, completely mastering the context regardless of distance.
This attention mechanism meant data could suddenly be processed in parallel, which created a massive snowball effect. First, you have the underlying mathematical transformer architecture. Because data could now be processed in parallel, researchers could do large-scale pre-training on huge collections of text. That created large language models. And finally, we put chat interfaces on top of them, sparking the global accessibility revolution we're all seeing today.
Section 6. Choosing the right tool. Engineering mindset. Which brings us to the ultimate takeaway. The core engineering principle you absolutely must adopt moving forward.
You know, there's this huge misconception that every new invention automatically deletes the old one. That simply isn't true. Look at this breakdown. If you have exact, stable conditions, rule-based software is still the absolute best choice. If you've got structured business data, traditional machine learning is incredibly efficient. For processing complex visual and audio patterns, deep learning is unparalleled. And for broad language generation, large language models are your go-to. The goal is absolutely never just to use the newest technology, but to choose the simplest, most reliable method for your specific specialized use case. AI is just the umbrella. How you choose to recognize patterns underneath it is entirely up to the problem you're solving.
Now that you understand how machines evolved from manual, hard-coded logic all the way up to neural attention, I'm going to leave you with this provocative thought to chew on. As AI continues to scale up at this breakneck pace, are all these systems actually equally capable, or do they inherently operate at entirely different cognitive levels, destined to perform fundamentally different kinds of work? Keep that in mind as you continue exploring this fascinating space. Thanks for joining me on The Explainer today, and keep learning.